This is Mr. Martin. These are the video notes for Honors Geometry, Section 1.4. This is going to be one of the most important sections that we've covered so far. We're starting with proofs. And really, we're going to be doing proofs for the entire first semester and a good portion of the second semester. And although we'll do other types of proof, we're going to mostly concentrate on two-column proofs. So I want to encourage you to get extra help if you're having trouble with these. As soon as you get the hang of it, it'll be a lot easier. But you know, it's not uncommon for students in geometry to struggle with proofs at the beginning. So again, make sure you get help as soon as you need it. Don't wait until after a quiz and you get a bad grade. So with that said, proofs basically is just a systematic method used to show that something is true. And then for our purposes, we're going to have certain tools of proof. We're going to use definitions, we're going to use postulates, and we're going to use theorems. So, you know, starting out with definitions, if a mathematical statement is a definition, then it states the meaning of an idea or term. Again, since this is the definition of definition, we talked about all definitions having a converse that is true. Okay, so the converse would be if a mathematical statement states the meaning of an idea or term, then it is a definition. So remember, to get the converse, we switch the hypothesis. So here's my hypothesis. Here's my conclusion. We just switch these to get the converse. Okay, and again, this is review because it's an important concept. All definitions are reversible, and reversibility implies that the converse is true. And then this is just a fancy word for reversible. Fancy word for reversible. Okay. All right, so moving on to our second tool of proof, we've got postulates. If a mathematical statement is a postulate, then it is assumed to be true without proof. Then we have the converse here, which you can read. And really the key idea here is that when you hear the word postulate, I want you to think assumption. Okay, these two words mean the same thing. So when you hear postulate, you just think assumption. We assume it to be true without proof. And most of the time, these are things that you're going to, you know, say to yourself, well, that's obvious, because they will be. So postulate assumption, that's our second tool of proof. And then our third tool of proof are our theorems. We'll have a lot of theorems this year. So if a mathematical statement is a theorem, then it can be proved. And we're actually going to prove our first theorem today in these notes. And then since this is the definition of theorem, we can write the converse. So if you want to pause the video and just go ahead and write the converse in, I'm going to save some time and not put that in. Make sure you check with me if you're not sure. Okay, so the process for using theorems, we're going to go through this a few times throughout the semester, but we won't always go through it. We're not always going to prove the theorems that we use. You know, sometimes I'll just tell you what the theorems are. If you have questions about it, make sure you ask, but we're not going to prove every theorem that we use the entire school year. But if we were going to, this is how we would do it. We would make a conjecture. A conjecture is just an educated guess about something we think is true. Okay, conjecture, educated guess. So then we will attempt to prove that our educated guess is true. And then if we can prove that it's true, then our conjecture becomes a theorem. Okay, so it's kind of like a bill becoming a law. The conjecture becomes a theorem. If you don't know what I'm talking about, then you probably haven't watched Schoolhouse Rock. Okay, moving on. Once a conjecture has been proved true, so we have this guess about something we think might be true. We prove that it is true, so it becomes a theorem. We don't need to prove it true again. Okay, so we just use the theorem the way we proved it. And we can also use that to prove other conjectures true. And we'll talk more about that in these notes. All right, so that's the process for using theorems. And one of the vehicles that we'll use to do proofs is a two-column proof. So we're literally going to have two columns set up. So we'll usually just divide our paper like this. We're going to have a statements column. And we'll have a reasons column. Okay, in the statements column, these are things you know. Okay, these are specific to the given diagram and the information. So you'll see that. So these are very specific things that we know or that we can conclude. That's going to go statements. In the reasons column, this is what we use to justify the statement. So if I put a reason in the a statement in the statements column, I need a reason to justify it. All right, so these will be theorems, definitions, and postulates that are going to go in the reasons column. And these are almost always in if-then form, conditional form. We've talked about that. There will be some exceptions, and we'll talk about those as we come across them. Okay, statements, very specific. We're going to talk about specific angles, specific segments, specific triangles in the statements. The reasons are very general. Okay, those are the theorems, the definitions, or the postulates. Again, if you have any trouble at all at the beginning, make sure that you get help and ask questions. All right, so let's take a look at an example. We're going to go through this whole process for using theorems, and in the process of our conjecture, we're going to do a two-column proof. So let's say we are given that angle A over here is a right angle, and angle D or angle E is a right angle. So we've got these two right angles, and if you want to pause the video, you can, but we want to make a conjecture about what we think might be true about all right angles, and more specifically about the two right angles that we have here. So the conjecture that you might make is that, okay, if this is a right angle and this is a right angle, then we could say if, well, let's just write it as sorry, let's scratch that again. Our conjecture might be that angle A is congruent to angle E. Sorry about that. So we're given that these two angles are right angles, and we want to see if we can prove that they're congruent based on things that we know already. And we have a few definitions that we've talked about so far in the first three sections that we're going to use to help us with this. So whenever we do a two-column proof, usually, most of the time, the information that they give you in the problem, so this information they give to us, we're going to put that first. So I'm going to put angle A is a right angle. Feel free to use abbreviations. That's given. So the reason we can write this in the statement is that it's given to us in the problem. And angle E is a right angle. All right, so now, knowing that angle A is a right angle, we need to try and make some sort of a conclusion about it. Well, since it's a right angle, we know that it has to be 90 degrees. So we can say that angle A equals 90 degrees, and the reason is, we're going to use our definition of right angles. If an angle is a right angle, then it is 90 degrees. Okay, and there's some slightly different forms of the definition that we'll be using throughout the semester as well. So since A is a right angle, we know it's 90 degrees. And since E is a right angle, we can say that angle E equals 90 degrees. And it's going to be the same reason. So if we've used a reason already, we don't need to rewrite it again. We can just say same as 3. Okay, and be very specific what it's the same of. Don't say same as above, because it could be anything above it. Say exactly which reason number it's the same as. So this is the same as 3. So now we have angle A is 90 degrees and angle E is 90 degrees. And we have a definition that says if angles have the same measure, then they are congruent. That's in one of our previous sections. So I can say that angle A is congruent to angle E. All right, and we're going to use another one of our definitions. If angles have the same measure, then they are congruent. So really what I have here in reason number 5, this is the converse of the definition. Converse of definition of congruent angles. So it's going to be very important that you realize whether to use the actual definition or to use the converse. So a couple more things I want to point out before we move on. If you notice, the reasons really are referring to something that's previously written in the proof. So an angle is a right angle. You could see this refers back to here. An angle is a right angle. And then the conclusion of each statement, then it is 90 degrees. You see it matches here. So the hypothesis refers back to something previous in the proof. The conclusion matches with the same statement number. Okay? And then over here, I've got angles have the same measure. Angles have the same measure. Let's try a different color there. Oop. Okay, that refers back to these two statements. Okay, refers back to these two statements. Then they are congruent. Here I have angles congruent. All right, so keep that in mind as you're going through that the hypothesis has to match with something previously in the statements column, and the conclusion matches with the statement of the same number. All right, I'm going to stop this video because it's getting a little long, and we'll continue this in the next video, which you could watch right after this one.